Okay, so welcome to our talk, and in this talk we present Unicorn, the next generation CPU emulator framework. You can see the rest of the website, our tool on the screen. Okay, short introduction. My name is Quinn. I'm a security researcher, and mostly I work on some very low-level stuff like operating system, virtual machine, binary analysis, and forensic, and so on. And I'm the founder of the Capstone disassembly framework.
Hello? 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 Can you hear me? Hello, maybe I speak here. So, my name is Wu. I'm currently a PhD student in CS, and I work on security for funds. I'm a member of VN Security, which is a Vietnamese security research group, the longest and strongest research group in Vietnam. Often I play CTF with dumps and write some exploit. The most notable one is the gains exploit that I published in their blog page. I also contribute to security open source projects. The two most notable one is Capstone and Peter. Capstone is Quinn's products for this sampler. You guys know about him already. And Peter is the GDB supported script that help you to debug and develop your exploit.
Okay, so here's the agenda of our talks. First, we introduce the background on the CPU emulator, what it is and what is the problems on the existing CPU emulators now. And because there are so many problems, we try to fix it and we come up with Unicorn engine. So the next part, we introduce the goals of Unicorn framework. After that, we go into the detail and the implementation and show you how to write application on top of Unicorn. And there's some live demo after that, and hopefully you guys can enjoy it and the conclusion. Okay, first part of CPU emulator. So, what is CPU emulator? CPU emulator is a software so you can emulate the physical CPU in software only. And here note that we just focus on CPU operation. We don't want to do full system emulation, but only CPU. And that's why Unicorn is just CPU emulators frameworks. There are many applications of CPU emulator. For example, you need CPU emulator to emulate code without needing a real CPU. So you can run your code on the emulator and you don't need the real physical machine for that. And for security application, we can use a CPU emulator to analyze the malware code. For example, most of the AV antivirus has some CPU emulator inside to analyze the malware code. So they run the malware code inside the CPU emulator, but they don't really run it on the physical machine, which is dangerous for your machine, right? And you can also use a CPU emulator to verify the code semantics when you reverse the code. Here's one example. Can you see that? Okay, zoom in. So you see that there are two codes, left side and right side. Actually, these two codes do exactly the same thing, but the code on the right side is much more simple and easy to understand. But the code on the left side is very hard to understand, very complicated. And actually, the code on the left side is generated by the malware. They transform the code on the right side to the code on the left side. So as a malware analyst, it's very hard to analyze, right? So the question is how to understand the code on the left side when it's actually very simple. So of course you can use a pencil, paper, trace to analyze the code yourself, but it takes a lot of time. So one good method is that you give the code on the left side to the CPU emulator and give the CPU context, the register value, the memory setup, and after that the CPU emulator will run the code on the left side for you. And at the output, you have the CPU context. So you can understand what the code on the left side does. So That's one very good application of CPU emulator. Okay, so how the CPU works inside? So given the input go in binary form, the emulator will decode the binary into instruction for your architecture you choose. And after that, for each instruction, it emulates those instructions to do exactly what this instruction does on the physical CPU, physical machine. So you need, at this step, you need to reference the instruction set manual of the architecture that you try to emulate. You need to handle the memory access, I/O, and etc. And after each instruction you emulate it, you need to update the CPU context every time you emulate every instruction. So a few examples. For example, on Intel 32-bit, given the input as 50, the emulator will decode this one into push EX instruction. And after that, it sees this instruction, you need to load EX in EX register. After that, it copy EX into the stack bottom. And finally, it reads the stack pointer by 4 and update it back, right? Just an example, if you see the emulator C01D1, it decodes this one into 8 instructions. After that, it loads EAX, EBX register in, 8 them together, and copy the result into EAX. And finally, it need to update on the flag register. So you can see that's all the work that CPU emulator does. Okay, so now you want to build simulator. It's not easy at all because there are a lot of work you need to do. First, you need to have very good understanding of CPU architecture, right? After that, you need to understand all the instruction provided by your CPU because you want to emulate everything. And some instruction has a lot of virus, a lot of side effects, and sometimes some instruction even not really documented. Like for example, Intel, they don't document all the instruction, so it's very hard to really emulate those instructions. So you can see it's very hard and a lot of work to build CPU emulator yourself. So the question now is, what is a good emulator? So you set some targets and you define what is a good one. First one, because now we work with, it's very common to work with all kind architectures, not only Intel, right? So a good emulator should support many architectures. You should support x86, of course, ARM, ARM64, MIPS, PowerPC, Spark, and so on. It should work on all the platform, not only Windows, but all kinds, Unix, Mac, Android now, iOS. Third is very important, it should be updated. Because the CPU vendors, they keep updating, they keep adding new instructions all the time. Like Intel, they add new instructions, CPU extension every year. So the good emulator should keep updated. So it supports even the latest instruction. The next one, a good emulator should be independent, which means you can use this CPU emulator to build your tools on top of that. So your tool just depend on this emulator. And finally, a good emulator should have good performance. So actually, there are two kinds way to build a emulator. The first one, easy, is interpreter. Interpreter works this way. Whenever you see one instruction, it decodes it, and after that, it calls some function linked with that instruction. Next time you see that instruction again, it calls that function again. So each instruction has one function, right? So it's easy to build an interpreter, but it's slow. The other way, which is way faster technically, is a just-in-time compiler techniques. So the way that when you see some code, we do not just code interpreter on the A rejection, but we compile all those code and we catch it. And after that, we run the machine code that we just compile. And next time, when you see the code again, we get it from the cache and run it again. We don't need to compile again. And that's why just in time the compiler, the emulator using zip technique is much faster. But the point that it's very hard to do that because you have to view the compiler. Okay, so looking at all the existing simulators you can find out, you can see that all of them have many problems. So we list some very popular one here: libemu, pyemu, IDA, x86, emu, and libcpu. So you can see that all of them only support x86 and nothing else. One exception is libcpu, which is designed to support all type architectures, but the project is died. Like it was last updated like I think 4 years ago. No more development after that. So libcpu I list it here, but actually nothing works with that project. Updated, nothing updated. Why? Because no single emulator you can see here support Intel 64-bit, which is very common and very important architecture now, right? Independent, libemu is built to detect Windows shellcode, so we stick with Windows only. pyemu is built in Python, which means you need to write your code in Python, so it's not really dependent. It's not really independent, right? You cannot write C and code in pyemu. IDA x86emu is a good plugin for IDA, but it's for IDA only. You need IDA to run it. It's not independent, right? This CPU is independent, but because it's like independent project, writing in C++, but it dies. You can use it. Just in time compiler, nothing use that, so everything is slow. On those emulators are very slow. So we dream to have a good emulator which have check in every line you can see here. You want a good one that support multiple architectures, always updated, independent, so you can build your tools on top of that, and using a zip compiler techniques, so it's fast. So yeah, you want a good one because everything we have now are not good enough. You want a good emulator which support multiple architectures on the popular one. You want multi-platforms running on Windows, Unix, Mac, Android, iOS, and so on, everything. You want it to be updated, support the latest instruction on every architecture. You want independent tools so you can view our tools on top of that. So it's best to have a good emulator writing in C, in pure C. And after that, on top of that, it support multiple binding languages like Python, Ruby, and so on. The good one should have good performance using zip. And finally, a good emulator should allow you to instrument at every level. Like you can do single step with that, you can instrument at this instruction, and you can intercept on the memory access, and so on. So all type instrumentation you should be able to do. So the problem is that until now, 2015, we don't have a single reasonable one. And apparently nobody wants to fix it. And we don't see any good future. Very sad, right? So until Unicorn was born, we decide to jump in and solve the problems ourselves because nobody does that. Okay, so next part, we introduce the Unicorn, the next generation CPU emulator. So the goals, like I showed in the last few slides, we want Unicorn to support multiple architectures, run in multiple platforms, always updated. The core Unicorn should be built in pure C and support multiple binding languages on top of that. So you can write your code using Unicorn in Python, in Ruby, and so on. It should have good performance using zip, compiler techniques. It allows instrumentation at various levels. Okay, so if we do that, we realized our dream to have very good emulator that check in all those things that we think that's important. Multiple arch, updated, independent, and fast. The problem is that it's very hard to build unicorn. That's our dream, but it's all at once. First, there are too many architectures. x86 only might take you like few years if you do from scratch. But now you see that you want to do everything, not only x86. And each architecture has many instructions. For example, Intel, the latest version has like 1,500 instructions. You want to emulate everything, it takes a lot of time. And instruction might have many side effects, so it's very hard and take time to properly emulate them. And finally, we have very limited resources. Because Unicorn started as my personal project, I can only do this in my spare time. So you can see that how is it possible. Next part is the design to Unicorn.
Hello? Can you hear me? Okay. So by now you guys should be already very curious about how we actually end up finishing this project, not finishing, but start up this project to the state as today. So I'm gonna talk to you about our idea and the challenges when we building this. So just to repeat what Quinn said, we want to have all of those wonderful features, but we want it fast, not like spending years working on it, and then we get bored, just like the lib CPU things. So luckily, we learned the lessons on Capstone, as Quinn said, authors, that in order to do this kind of thing, we should stand on the shoulders of the giants. Meaning, we should choose some existing platforms or existing softwares and try to take advantage of it. Just like Capstone, take advantage of LLVM. And the second thing is that we need to open source these things so more people can get involved and help us to improve the products. So we're looking for various places, various emulators, existing emulators, and something that look like emulators. We even think about using Capstone to build this thing because Capstone has a very good disassembler. But the thing with Capstone is that it has is lacking of semantics. So it's hard to, you can get the instruction out, but you need to understand the instruction, what it does, like on kind of flags that it changes, how it accesses memory, and so on and so forth. And that thing is also a lot of work. So this is our idea. We use QEMU. So for those of you who don't know about this project, it's an open source project for building system emulators. It's been around for more than 10 years with a lot of community involved, and it's updated like almost every week. And as we look at their repository, so it's highly active. It supports multiple apps. So in total, we count is total 18 architectures. So it's a huge set of code. If you just run slog counts in their repository, it's like a few millions of codes. So it's a huge project. It's work on multiple platforms. They build their Makefile system so that it can compile in Linux, can compile in iOS, can compile on Windows using cross-compiling tools. So it sounds like a very good candidate. However, QEMU, as I mentioned, is a system emulator. It has all kind of things in there. It has emulation for IOs, for peripheral models, memory, some hardware you can plug in. It has some debugging tools that attach to it, and everything's mixed together like spaghetti. So it's quite challenging. So why we choose QEMU on those seems to be overkill. We see that this is the only tool that have all the features that we need. It support all the type architectures and very updated. It's already in C. So writing Unicorn on top of it is okay. It has cheat in the CPU emulator, so it's quite fast. It also have optimization on top of cheat, so we can make use of them, as our feature as well. But so, are we done? Can we just like check that thing out and that's it? Can we just fork those and that's it? The answer is no. If you ever work on Capstone at the initial stage, you will understand that refactoring code and taking out things is a huge problem. So we need a lot of things to do. We need to understand the code. And if you look at their code, it's like 3 million lines of code. It's really difficult. So there's definitely some challenges that we want to solve. So let me list some of the most challenging problem that we found while building Unicorn on top of QEMU. So the first challenge is that, as I mentioned, QEMU code base is large. It has everything in there. And the thing that we want is only actually this little red box you can see. We want the cheat emulator, simulator on top of it, and some component that can help us to emulate the memory access. That is the software MMU. So our job is that we want to keep this CPU emulation code and remove everything else. We need to understand all the codes and just take out what we need, and hopefully the part that remaining is easy to understand and easy to work with. We need to keep to support all the subsystems that they have that already really integrated deep inside each architectures, like the Q objects. It's just like emulating some C++ class. And then we need to rewrite some of the components to keep this CPU component code intact. Why? Because we want to like update to the upstream, which is QEMU code, whenever it releases the new versions, or like whenever there's a bug in QEMU, we want to fix it in our code as well. And on the other hand, any bugs that we found in our library, we can report upstream and then help them to fix. So the second challenge that QEMU is set up emulators. They have on-cap architectures, but they compile into individual binary. So each binary can only be used to simulate one architectures. This is decided the compile time. So after you compile, you have no way to emulate it, other architectures. So what we want is that we want to have a single simulators API, a framework that can support on-cap apps. And we should allow the user to choose what cap apps they want in their code. Just like Capstone, like you just put in the Mac files, like I want this x86 only, or you want just ARM only, or you want ARM x86. This, if you think about it, this is the application is very simple. Like you have just a bunch of binary, you don't know what it does, what kind of arts you want to run on. You can just run the emulator on different arts and see what they do on different arts. So we isolated also because QEMU has only individual binary, they reuse the variables everywhere. They reuse data structures everywhere. So this is not good because it's not thread safe. If you just run multiple instances, it just reuse the global state, and therefore you got conflict and so on. So we isolated all of these variables, structures to ensure our API is thread safe by design. We also refactors to allow multiple instances of Unicorn at the same time, so you can just spawn a lot of thread runnings, Unicorns, or you can create a different Unicorn instance that can emulate for different arcs in the same binary. Also, we modify the build system to support multiple arcs on demands. So the third challenge is that QEMU has no instrumentations. Actually, it has instrumentations, but it's come as a static tools. This means that if you want to instrument some instruction, you have to add your code at compile times. You just add your code, and then they will compile into the binary, and from the binary, you can execute your instrumentation code. And also, cheat optimize is very bad. It's used on the tricks, on type tricks. It's cleaning the code. It's like do dead code eliminations, that kind of things. So if we just insert our instructions and then the cheat optimization clean it out, we won't be able to work with it. So in this aspect, we write our instrumentation layers from scratch. We support like single step. We support instrumenting on memory access, like read and write. You can detect whenever memory is read and writes and executes your callback. We can change the register dynamically at runtimes, in emulation runtimes, and we also be able to handle exceptions like interrupt system call. Like if the malware code even calls some interrupt to execute a system call, the user can capture that and execute their callback. So the fourth challenge here is that QEMU is leaking memory like crazy. It's like when we look at the code, we say, okay, this memory was open, mallocs here, but there's no close, there's no free. So if you just run a simple one line over QEMUs, there'll be tons of memory leak. But this is 5.4 tunes as a QEMU because you just run it once and then you just close it and that's it. But for framework, we need to fix it. Because we want the user to be able to run it multiple times and maybe just stay in the memory for a long time and running on-demand code that was passed in. So we need to fix on this. So we fixed most of it until now. And we also refactor all of the subsystem so we can keep track of this pointer from where they are logged and clean up on the lingering pointer when we finish. So to summarize, we fork QEMU, but we already on far beyond it. It has become an independent framework. It is much more smaller in size. So right now we have only 200,000 lab code compared to a few million lab code. It's lightweight memory. We just keep those that we need and we clean up the memory. It's thread safe. You can use multiple arcs at the same time. It has good interface for implementations, and we can, because it's our own code, we can build on top of it. It's more resistant to exploitations. This is more secure. So this is slightly oversight, but because what we figure out in practice that there's a lot of QEMU exploitations on the CV that we found, but all of them is like it's peripheral part, the hardware that attached to QEMU, but the CPU emulator actually is never exploited. And on the other hand, because we write as an API, you can write unit tests for each individual components. You can write integration tests on cap tests. You can fuzz it, like it's fuzzer is on around nowadays. So it's very easy to test, very test friendly. So now I pass back to Quinn so he can show you how to write code in Unicorn.
Okay, so in Unicorn we have framework, right? Now you want to build your own application on top of Unicorn. And we have a set of API provided by Unicorn. It's very simple, clean, and easy to understand. You can see that later. And the core Unicorn provides API in C. So with API you can open and close Unicorn instance. You can start and stop emulation. You can start emulation and run until it hits some instruction. You can run until it like some amount of time is happen, and or you can run until a certain number of instruction is hit. And the API allow you to read and write to memory of the emulator. It allows you to read and write to registers. It has some memory management function. You can hook memory events, so you can find, for example, when some invalid memory access happen, so you can act accordingly. And it has also some API, so you can dynamically map memory at runtime if you want that. So you can handle invalid or missing memory. And it has some API, so you can define the user callback. So you can instrument at instruction level, you can do single step, you can intercept all memory event, read and write. And on top of that, on top of the C API, you build the Python binding. Python binding is available now. You can use that to build your tools. So here's one simple code in C. I will just briefly introduce. You have UC open to initialize the engine. So here you can see that I want to have an engine for x86, 32-bit, right? Later, I have another function, UC map to map memory inside the emulator. After that, UC memwrite can be used to write the code you want to emulate into that memory. You just map. After that, UC write you can use to write some value to the register inside your emulator. And finally, you can start emulation with UC emu start. Here, for example, you see that I decide to emulate my code of this size, and it should run in infinite time, and I don't care about number of instructions. Run until finished. And after that, after emu start, we finish emulation. And after that, I read out the old register and print out with UC read. After that, print out later. And you have one function to read from memory, UC mem read. So you can see that I can read from the memory of the emulator. Okay, the same code, but written is in Python, which I think much easier, much shorter, easier to understand, shorter. See here that I initialize the engine. So I open the engine in x86 and 32-bit. After that, I map memory in 2 MB. After that, I write the machine code to be emulated to the memory, memwrite. After that, I set up the register. Here I set up ECX and EDX registers. After that, I run the emulation. And this one stops until this arrest is hit. Finally, I read all the register out, ECX and EDX out, and print out. So you can see how the register is changed after the emulation. And finally, I read from memory, 2 bytes, and print out. That's it. Simple, right? Okay, so I have some live demo here. So you can see how it really works. Okay, so here's on a simple code in Python. You can see that. So here, the problem is that I have one bunch of instruction that I don't know what it does. It's from some shellcode I got on the internet. Here, some bytes. Another question is how to know what this shellcode does. So the idea is that I use Unicorn to write this script. And here, you can see that I did exactly what I showed before. I initialize my emulator in x86, 32-bit, map memory in, write the shellcode into memory. After that, I set up the stack, ESP, stack register, to point to somewhere that some memories that I already set up. And after that, because the shellcode may call some interrupt, which in the Linux case is an interrupt AT, right? So I need to hook the interrupt so I can get notified whenever the shellcode call the interrupt, so I see what it tries to do. And after that, I run the emulation. So you can see here what my interrupt hooking does. So the idea is that when the interrupt is called, on Linux, the interrupt number is 80. And when the interrupt is called, it set up the function for interrupt for support. If function is 1, that is exit. And the function number of the interrupt is defined inside the EAX register. So I can, when I handle the interrupt, I read out the EAX here. So when the function is 3, that is read from some file in the system. When the function is 4, that's the shellcode try to write something, all right? So now here, I show you what this shellcode does. I run the script, I just show you. We try to emulate the shellcode. See? You can see here that this shellcode try to create a socket, the network socket, and connect to somewhere, some machine, somewhere on the internet. At this address, 127.1.1.1 at port 12345. And after that, it duplicates the handle of this socket. And after that, this shellcode open the etc password file. See? And next, it read out everything, which is 64K. That's, I think, enough to read everything inside the password file. And finally, it write to the file descriptor, which is a socket, which means this shellcode try to write the content of password file to the socket, and you can send it to somewhere on the internet. So, in short, this shellcode try to steal the password file and send it to somewhere outside on the internet, and after that it exits. So you can see that it's very easy to emulate the shellcode and see what it does using a very short and very simple script using Python and using Unicorn like that. So you can say that, okay, I can, if I given the same script and the same binary code, I can just throw into the IDA Pro and see what this shellcode does. But it's not that simple, because if the shellcode is shell modification techniques, which means the shellcode can generate some code at runtime and execute the code that is just generated. You cannot just throw the shellcode inside the IDA, because IDA only handles the static analysis, right? You cannot handle shell modification code that's only generated at runtime. But in this case, Unicorn works very well because we really emulate the shellcode and we run it so we can see what happened at runtime. So that's the first demo.
Thanks, Queen. So Queen asked me to write some fun things for you guys because we all like fun. So the first thing is that, so if you guys ever play CTF, you already know DEFCON. So there's a problem in DEFCON named get question, which asks us to, they provide a binary and also the initial state of the register in x86 64-bit, and asks us to emulate that code and then return the ending values of on the register at the end of the runs. So a lot of teams play in this challenge, and they have some write-up. I think still have it online. So a lot of write-up, they just they try to, here in this particular case, they put it in their own assembly code and then compile it in a real x64-bit, run that code, and print out the results for them. So when I play this challenge, what I do is I find x86 machines I write some GDB script, and then I change the register variable during debugging time, and then let it run for a while. But during the times we already starting to use Unicorn, so I decided to also write some code in Unicorn that do the same things. But look, I think it's more intuitive. You just, the same thing as Queen does, we initialize it, memory map it, some register that provided to us by the challenge, write it to set up the stacks, write it to our address, and then emulate, and finally just print out the register at the end. So let's just try run, see whether it's really work. Yeah, so it's done, it's print out results at the end. So this is first demo. It's look like on the consoles is it's not very intuitive to see, so Quinn also asked me to write some fun codes. So we go to the internet and see there's a guys that write an emulators in the browsers and try to emulate code in the browser and display the things during you can click and then see how the register change. That's really cool. So we just want to make something similar, and I just write it up for a couple of days ago, and hopefully it still work. Okay. So this is the interface. We just reuse the interface that Enigma, this tool that built on top of Capstone to this assembly. So let me put some code in. The resolution is bad, but you can see that we can disassemble the code here for you to see. What the code is very simple. You just move some values to the register, move it to the stacks, move it back to the register, and then add them together. So let me just single step it. You can see this instruction move one to the register RCX, and it's changed here. The IP also changed to the next instruction with row 7, as you can see it highlighted. And we just emulate. And finally, it's add IX and RBX together. So you should see number 4 appear here. Yes. So you can emulate again. You can change the values at runtime because it's supported by Unicorn. For example, in this case, REX and RBX is 2, so we can just change to something. Yeah, maybe it's too easy. Yeah, correct. Well, good. So thanks. So we have a demo with self-modifying code as well, but I'm not sure if we have time, so I just quickly saw an ARM test. So the same code, but this is ARM architectures. Just emulate is changing because the PC is always R15 plus 8, so nice. You can see it, there's just change, it's moved 10 to R2 and so on and so forth. So the same idea work across multiple architectures. We can also solve memory here, but I'm lack of time, so that's it for demos, I think. So let me quickly go to the end of the slide, and then we go to the questions. So right now, the status of the work is that we support 8, 9 architectures. There are 7 architectures. We have Python binding, which is based on QEMU 2.3. So our future work is that we want to support all the rest of architecture that QEMU support. We have experience on how to move code from QEMU to our code, so this should be fast. We want to stripping out more utility codes from QEMU. For example, we want to improve their assembler. Maybe there's some integration with Capstone for the one that they support. We want more bindings. This is promised by community, just the same way as Capstone. We want to synchronize with 2.4 when it's released. And the point is that the future of Unicorn is guaranteed because people are still working on QEMUs. So in conclusion, here's a summary of our Unicorn frameworks. You can read the slide. We're serious about committing time to this project and make it the best CPU. So we hope that after we release, we can have help from the community, just like Capstone, and we can make this become the best emulator. And on the other hand, if we make this the best emulator, QEMUs also benefit from it. We can report upstream, singing it to our code, and make it the best system emulators. So that's it for.
Okay, so that's it. Any questions? Yeah. Sorry, I cannot hear. Mixed instruction in ARM? Yeah, of course. So whatever you can run on the physical CPU, you can do that inside QEMU.
Yeah, so can you hear me? Yeah, okay, so you know how you initialize it with 32-bit or 64-bit? What if the shell code is like mixed mode?
Oh, that's only the initial phase. After that, you can switch inside.
Oh, okay.
Runtime. There's no problem.
Okay.
Over here.
Yes.
So on your mem map, you don't appear to support memory page permissions. Is it supported? Do you intend to support it? Can you generate faults when you try to execute out of a non-execute page and so on?
Yes, definitely. It's on our roadmap that will be supported very soon when we release. Yeah.
Okay.
It's because QEMU has system for handling permissions. We just use the default one, so we can change it.
Okay. And what's your process for making sure you stay synchronized with all the QEMU changes that go on? You just constantly combing through their patches and pulling them over, or how's that work?
How long do we update?
You mean how long what?
We update to the QEMU option.
I think it's not very hard, so it should take the little time to do that.
Okay.
Okay.
Hello? Okay, so how far are you from doing symbolic execution instead of concrete execution the way you're doing it? Can you get to a point where you can just leave a register undefined and then go through the operations that happen on that register?
Can you repeat question? I can't hear.
Everything I've seen here is concrete execution, so you give registers a value and then you run through the binary.
Yes.
Do you have in mind, do you have any plans to implement some kind of symbolic execution on this? So instead of giving it a value, just seeing what happens with it?
Oh yeah, that should be another project, right? Because in this project, we just focus on CPU emulation. So everything else is CPU on top of that, and we don't intend to do that in this project.
Okay.
It's not only about CPU emulation. But yeah, there are a lot of operations you can build on top of that. Yeah.
Hello, I'm asking about possible blue pill and red pill, blue pill detection and red pill. Do you emulate CPU side effects like cache misses, performance counters of computation? So.
Okay, that's a good question. Because actually now we just take whatever QEMU does, whatever QEMU has. So if QEMU doesn't do what you want, which means we don't do that. But after this phase, I think we can look at the problems that QEMU cannot do and see what we should do to improve that on top of that. So yeah, so far, whatever problem you see in QEMU, we also have that. But in the future, we look forward to improving it.
Hi. Do you expose in your API the ability to set the length of the instruction to coding pipeline?
No. So far you can see that the API is very simple. It only allows you to emulate the code, that's it. And we try to keep it very simple. And for more complicated things, I think we can see how we can extend that, but so far, maybe not.
Okay, thank you.
But because it should be open source anyway, so we can extend it to do whatever we want. And if we think that it's suitable for unicorn project, we can put it back. Otherwise, you can fork it and do whatever you want. Any other questions? So the final question is that people can ask where you can get the source code. So the problem is that still we have some issues that we try to fix now. So we want to play with unicorn, just contact us. So we've officially opened the beta test from today. So if you can help, if you can go, you want to test, contact us in those areas on the screen, and we get back to you. And after the beta test phase finished, we officially release everything to the public, and the license of unicorn will be in GPL.
I think that's it for our presentation. Thank you very much.
Thank you.
You can stay for ask questions if you like.